For this talk, we have Network Layer Confusion, Fun at the Boundaries by JoshuaDeWald. So please take it away.
All right, hello there. So like it says there, this talk is called Network Layer Confusion, which is intended to kind of have a couple meanings. One is that if you're like me and you were essentially an application engineer or backend engineer, network layers are confusing. You sort of forget what they are, and it's hard to keep track. But also that there's a lot of interesting stuff that happens in the boundaries between the layers. So you get confusion within the layers, and that's sort of what my talk's about, and I hope to go over some of that stuff. So as a quick intro, my name is JoshuaDeWald. I've been a professional software engineer for about 20 years. My last 10 years was at a edge computing CDN company with doing dev and SRE. And that's sort of what led to this talk was I know one of the common things here is liking to break things. I don't like to break things, but I like to understand why they're broken and try to predict that they will break so I can help them not break. I'm currently at Recorded Future, but this talk is completely independent of my work there. While I do have network certification, I am very much not a network engineer. The last part of my work at Prior's company was doing engineering of networks via BGP and SFlow and stuff like that. So I do have a background in that, but I'm definitely not a network engineer. I'm also not a security engineer. This is really not my, I don't come from cybersecurity. I come from the dev ops background. But there's obviously a lot of overlap because a lot of what we're doing is trying to protect things. And fundamentally, I find this stuff really exciting. I actually I think networking is really cool, and I think there's a lot of fun stuff with it. And I'll show my email again later if anybody wants to contact me. I'm on GitHub and whatnot. So what I hope you learn is, if you don't know anything about networking, I hope that at the end of this you know more and you have more things to explore. So throughout I'm going to kind of give some ideas, but I'm also going to give you topics that you could look into. I hope that even if you know networking or think you know networking or have been dealing with networks for a long time, that you see stuff that surprises you or that you hadn't at least thought about that way. That would be awesome. I'm hoping that you see that the network layer abstractions cause surprising impacts. And that you see that there's a lot of trust in networks that might actually really be surprising to you as we go through. And networks I found that there's almost more below the stuff most of us application engineers deal with. There's actually a lot more below that than there is above it at the network level, and that kind of shocked me. And obviously, part of the talk is called about request smuggling. So obviously, I want you to understand smuggling attacks and where they come from. So as a quick refresher, what is request smuggling? So it relies on the idea of an intermediate system. So you're sending some request to some system. Usually it's going to be an HTTP request, but it doesn't have to be. And you're not actually talking to the endpoint that's serving your request directly. You're talking to some intermediate system. And so what can happen is that you can interpret those requests, the data differently. And that can lead to request smuggling, right? So you can do something like a desync where you've sent one request to a front end, but the back end sees two requests. And you can use it for making otherwise forbidden requests. You can use it for cache poisoning or credential stuffing. Kind of more specifically, let's say there's some secret site that you're trying to get to. It has some valuable credentials, some valuable data, or maybe it's an unauthenticated API that you could send some data to maybe add yourself as a user or add some sort of a basic thing. And I'm sure every one of us has been at companies that might have those. It's like, oh, we only allow internal people in. We have a firewall only if we block on certain IPs. That's the only way to get to this system. And we also have a load balancer in front of it that doesn't know anything about that backend server because it'll only serve the public site. It has no idea how to get there. We're totally protected. And so really the end point of this talk is about how would an attacker get through that. But at first, as I said, we want to talk about introduction to networking. So probably a lot of you guys are aware of the OSI layers. Quick hands. Everybody know? Have you guys heard of these? Who hasn't? Cool. So the idea is these were kind of conceptual layers so that's why there's like no layer 6, because the OSI was this model that didn't really get used, but a lot of stuff ends up lining up nicely with it. So we have the medium, the layer 0, sort of the actual medium that we're going to put stuff onto, copper, fiber, wireless. We have some encoding of bits onto that, layer 1. We can link together systems to create a local network at the layer 2 level. Then we can start connecting those networks together with addressing at layer 3. We can add flow control and stream processing at layer 4, TCP, TCP and UDP, which probably most people, this just starts to get into where most people operate. The session layer, you could argue TLS is over there, and then the application layer, which I assume is basically where anybody who's dealing with systems, a lot of penetration testing is really going to happen at layer 7. But you notice that that's the top layer of this thing. That's the last thing. There's a bunch of stuff that makes that all happen. And so, like I said, you start with this layer 0. You have some analog medium, you have copper wire or air or glass or something, and you're going to put an analog signal in there, some sort of waveform. And in the case of string, maybe you put some vibrations on it. You do electromagnetic radiation, you do light, you do electricity. And then you do some sort of encoding to make that look like bits. So this picture is actually from the original Ethernet standard from 1980. So this is defining the 10 megabit Ethernet, and it's showing sort of how you would pull that out. So one thought I had while making this talk was, could you do weird things even at this layer? Like what if, so there's these different encodings, Manchester encoding. So it turns out that Manchester encoding actually has 2 different ways of encoding bits. So as your signal goes, it goes back down to the base, and it goes up to encode a 0, and it goes down to encode a 1. But it actually turns out there's another version that goes the other way. So what if somebody in the middle thought that you used one, but you're actually using another? And so you could, even just at this level, you can, the fact of the matter is, the outcome of those bits is, the interpretation of those bits is a artifact of the agreement between the systems talking. But let's start getting into the part we're going to start getting used to. So we've got these systems wired up, let's just say with a a Cat5 cable, which is sending this stream of bits over it. Well, that's not going to be all that useful to us. So we need to start delineating portions of those bits into frames. So we're kind of going to use timing and other information to decide where we're going to determine that, hey, I think this looks like a message, and we call that an Ethernet frame, right? And so each of these is going to have some hardware address that it's going to look for, a MAC address, to determine how that message, who that message is meant for. And one thing you may notice on this is that 1500 byte MTU, known as the maximum transmission unit. That's the idea of that is this is the maximum amount of physical data that we're willing to accept. And I always wondered about that value because any of us who deals with networking, it turns out this is comically inefficient in today's network. So this was designed for 10 megabit networks. And so you're sending one packet at 1500 bytes, but meanwhile you're on nowadays you can do 100 gigabit networks or even a gigabit network. But I still wondered where did that value even come from? And it seems like if you do the math, that with a 10 megabit network, that 10 megahertz signal, it's about 9.6 microseconds per bit. And if you do the math, it works out to be about 1.25 milliseconds for something to wait for a signal. Then get you 1,500, a little over 1,500 bytes. And so that seems to be about where that was. With these clocks from 40 years ago, which is basically when I was born, we're still dependent on that, and that's why you see those smaller frames these days. There's actually controversy over where that value comes from, but that's what I sort of found. But as I said, one of the things about that is that they had to wait for that 1.25 milliseconds or whatever it is. And that's because the original design of Ethernet was a shared medium. And we still treat it like that. And it acts as if that. So the idea is, if I were to send a message over this shared bus, and probably a lot of the people here used to have hubs, right? We'd go and get a hub. You'd hook in and you do a packet capture, and you could see absolutely everything. And that's because those were literally just connecting the wires together between. There was no logic. Those things had zero those had zero intelligence to them. And so these days, though, you notice we use switches, right? Switches actually allow full duplex. So with those hubs, you could only, if you had a 10 megabit network card, you could either do 10 megabits up or 10 megabits down at any given time. Switches, since they can buffer the messages, they allow for full duplex communication. They're controlling what's going over the wire. But now, with this device that isn't broadcasting every message, it has to then, if the one on the left is sending to the one on the right, it still has to figure out how to get that message over it. So let's say that top one sent a message, to the one on the bottom. And so it gets to the switch, and the switch has no idea. It's never seen a message from that one on the bottom. But now it's seen a message from the one on the top. So this is what's called MAC learning. So within your switch, it'll go and it'll see, this one on the top left sent through my ETH0 port, sent a message, and it had this source MAC address. I now know where I can probably send messages destined for that. But it still doesn't know how to get to the bottom. And so what it does is it does what's called flooding. It floods out those messages, that exact message out over to every port that has something connected to it. And so ideally, you hope that the one that actually it's targeting will receive that message. So on the bottom of the right, you can see it does. And so now, that bottom one, it gets the messaging, it can respond to it. But now that it knows where the first one was, that message kind of flows right through the switch. Other devices don't see that message, and now the switch knows where number 2 is, and now those messages are quote unquote private. But note that, but still it's a shared medium, so there's a notion of broadcast addresses. So if you've ever seen the FFFFFF, basically a MAC address that's just a bunch of Fs, right? All that's sort of a special one, but the actual only fundamentally important part about that is that the least significant bit of that MAC address is set. When that bit is set, it tells the switch to just forward it to all the other ports. It makes it a broadcast or a multicast address. And so you could use that you could send messages setting that bit as your destination MAC address and have those flood. So if something wasn't looking for that, that's one way you could disguise messages, is to send over non-standard broadcast ports or MACs. Or if you want to send messages to something that you don't want anybody to know who you're sending that message to, simply make up a destination MAC address and have the message be something that the other side is willing to recognize. Or maybe the payload's what matters. And so this is where the idea of, if anybody's done Wireshark or packet captures, the notion of promiscuous mode. All that means is, when you're in promiscuous mode, it's willing to look at packets that have a destination MAC address that doesn't match the interface that it's scanning on. And by default, because those messages can make it. So even at this level, we can send messages that never even touch any other layer. So we can send messages, and so there's a demo of that I do link in here, and there's a link later, where I essentially just created a very simple layer 2 chat application. It allows anybody on the local network, you just fire this up, and you can start having conversations that never touch layer 3. And so if a packet capture was looking for layer C messages to see who's talking to each other, they don't see any of this, because whoever packet captures with the -E does a TCP dump with -E. I'm guessing mostly nobody. But this also, that learning allows for hijack. Because remember, the switch does not enforce MAC addresses. It simply learns and observes where they are. So what that means is that if you send a packet and you source it from a MAC address of a device that you would like to receive messages for, you simply source it for that. And then as long as that's not sending messages, or even you're going to fight with it, the switch will happily send you those messages. And so I show a demo of that with also the layer 2 chat application, where in the same one, but added. One thing to also know is MAC addresses will look essentially random, right? They're not very good for, as soon as we leave the network, they're not very useful. The first 3 octets are essentially refer to the manufacturer. It's called an OUI. So you can use lookup tools to, if you have a MAC address, you can see who made that. But that ability to spoof is not some weird malicious thing. That's how VMs can work, right? If you're on any sort of hyperscaler, if you're on any sort of hyperscaler, those are necessarily going to need to send arbitrary MAC addresses. But you can protect against this with what's called a managed switch. So if a switch advertises VLANs, it's probably a managed switch. The ones you would get at like Best Buy, those are going to tend to be what's called an unmanaged switch, which just basically means you plug it in and it works. With a managed switch, which costs a little bit more, you can enable what's called port security or MAC move protection, which basically will detect that a MAC address has tried to go to a different port. Or you can also do things like statically allocate. And then you should always reduce your broadcast scope. Be aware of the fact that if you have everything on the same layer 2 broadcast domain, in theory, every single message is being conveyed to every other device. An attacker could obviously use that broadcast messages to saturate their own interface. So you could saturate and send a 1 gigabit of data, but if you make sure it's broadcast MAC traffic, then you could flood that over out. You use the switch to saturate every other port on the switch. If you want to learn more, I definitely recommend you look at VLANs. That's actually what got me into this, is people kept talking about access and trunk ports, and I had no idea what they were talking about. Learn about RSTP, which prevents these switches to forward into forwarding loops, which is very, very bad. LLDP is how you can actually see who is in your local area 2 network, including port names and whatever the device advertises. So all network devices support LLDP. And MACsec is also a way of preventing this, where you can do signed layer 2 packets, essentially. So it's sort of a secure MAC 2. But it's not really that interesting to, as we start having more networks, that's where you're not really going to make an HTTP request that much, locally. You're going to want to start to talk to other networks. So these could be physically separated, or they can use VLANs to separate them. But how do they talk together? And the short answer is they don't. At layer 2, you cannot talk to different networks. If you can, then they're the same network basically by definition. So even if you have the same physical switch, those can be physically isolated through what's called those VLANs. So how do you connect them together? And that's where layer 3, where it starts to be where we're used to operating, right? IP addresses, you add networks, you can start connecting networks together. And so IP addresses allow those hosts to be reached in an easier way. But one thing is to not think of it as an identifier. I think we have a tendency, or maybe I just do a lot. Anytime I say confusion or anything, this is the way I've always thought about the world. I've always kind of thought of it like, this is my IP. Like, this is the machine, I have this IP. It's really not. It's actually more of like a routing artifact. It's an easy way of getting a message to whatever to your layer 2 machine. And you can even have multiple IP addresses. And so really it's not identifier. And so I think getting away from that idea can help you think better about networking in my view. And so how do you get that IP address? So you could statically allocate. You can literally, again, they're not special. You can go onto your device at any time and just give yourself whatever IP address you want. Define your layer 2 subnet. That's going to be that slash after the interface address. Or you can get it from DHCP. So I think we all kind of think of DHCP as like owning that assignment, but it doesn't. What happens is, and I don't have a slide for this, is you broadcast a message saying, I don't have an IP address. Will somebody please tell me what IP address I should use? It does not assign that IP. It simply says you are allowed, like, I think this could be one that's unused. You get that, and then you respond back to that server saying, yes, please, like, acknowledge that I'm taking that so you don't hand that IP out as well. And then that DHCP server responds with, cool, that's good. Also, here's your default gateway, and here's your DNS addresses, and also here's potentially random routes that I also want you to install, or actually a ton of other things. It's actually remarkable how much DHCP does. We're used to think of it as like, well, the DHCP wow, I cannot say that word, gives me IP addresses, but it doesn't own them at any time. It's just another device on the network. And so as we were saying, like we're trying to talk over, really fundamentally, we're still talking to devices at layer 2. That's how we're actually connected. You don't buy an IP cable, you buy an Ethernet cable. And so we have to put those IP messages, this was called encapsulation. We take that data that we would like to send, this IP packet, and you'll find that most frame formats look very similar. Destination, which makes it, so if you think about if you're hardware processing, you want to have the very first bits you see tell you what to do with it. So you put the destination first, you put the source, and then here you put the protocol and length and protocol data. One thing I didn't mention, there is no length header in Ethernet. Now I show this as type length, but that's kind of a lie. Any length over like 1500, or I can't remember the actual value, is considered a type field. And that's what we use in all modern. So if you look at IP, it's like type 0800, and I think IPv6 is like 8806 or something like that. So the length is still going to be determined from the timing. It's still going to be based on framing, based on random attributes of the bit stream. But in any case, we are going to go and we're going to write that data over MAC. Now, you may now be wondering, but we have an IP address. How do I know what MAC address to send to? And remember, we're always talking over the same local network. So this is where address resolution protocol comes into be. So this is known as ARP, right? I think I had always heard of ARP growing up, or sort of as a developer, I had no idea what it was there. It was just kind of magic. Every once in a while, I'd see a packet capture that maybe had it, and I didn't know what it was. So what happens is you send to that magical broadcast address. So let's say, again, that top wants to send to the bottom one, but this time he wants to go a layer up and use layer 3. So he sends an ARP packet that says, hey, it shows in packet captures as who has this IP. I would like to reframe that as who is willing to claim that they are willing to handle this IP address. And please respond with your MAC address. And so right now he has an empty ARP table. And if you're on Linux or maybe on I'm not sure if Windows will do it, you can just type ARP and you can see your ARP entries. So that once again, that'll get, hopefully the switch will broadcast out to everybody. And then the one that actually, in theory, has it, again, if this is a normal network, the one that has at some point decided it has that IP address will respond with its MAC address. And the host one will add it to its ARP table. And now, next time it needs to send to that IP address, it'll use that MAC address. But remember, just like MAC, you can spoof the MAC address, right? Anybody can respond to that ARP message. So again, there's nothing in a protocol that you don't have to sign your ARP message. Anybody can say, yeah, that's my IP. The DHCP server itself could be a rogue DHCP server, or anybody can respond to that. So we've barely gotten into the local network, and the amount of things that an attacker could do is kind of amazing. One thing I do want to note, nothing I'm saying is new. This has all been known for the entire era of networking. Anybody who's been in networking knows every single bit of this stuff. But I know that I didn't know this stuff as essentially an application engineer. And so this stuff is I think, important there. I want to take a quick side trick on I know this is probably a horrible slide, on IP addresses themselves, because I think they're kind of interesting. So this is an example of Google.com. And I only chose this because they have enough infrastructure that they're not putting, this Google.com itself is not behind a multiple vhost domain, or at least Google.com is the default host for this. So what is that really? It's really a 32-bit number in binary, right? We tend to arbitrarily frame it into these individual bytes that we write out as these 4 octets, and that's kind of how we're used to looking at it. And so we have these binary digits. Now, it's actually this number, 2,398,804,356. You can just put this into your web browser, and you'll get Google.com. You could curl it. I mean, this is really what an IP address is. That nice thing we see, computers do not care about. They only care about how they can match it to assignments. And we're probably most of us have seen a lot of these things. So I just want to quickly talk about RFC 1918, which essentially defines private addressing. And these are addresses you should never see on the public internet. That's why when you're at your home, so the 10.8, which basically just means anything that starts with 10, so this first 8 octets, and then anything else. 172.16/12, so you notice the /12. So what that means is the 172/16 and .17 are both within that private space. And then 192.168/16, which we're all kind of like every single home router probably in the world uses that, and it lazily uses usually the 0.1 network. But you actually have 65,000 different, right here you have 65,000 possible IP addresses within that, and you can break it up into however many networks. And you can choose to break it up however you want. That's the great thing. And also the loopback is /8. I think this is interesting. So again, growing up, or you think 127.0.0.1, that's localhost. That's my localhost address. Well, the actual interface has an entire /8 associated with it. So while 127.0.0.1 is what you would sort of source your packets from, you can have any service listening on any of those other addresses. Or if they're listening on if they see they're listening on the undefined, then you can hit it with any of these addresses. I think this is useful for troubleshooting. So let's say you're running a bunch of services, and you're like, oh man, I've already used port 8080. but I want to hit it over localhost. Well, just hit it on a different port, and you can even bind it to the other port, and then you can safely have multiple services running on the same port on local because they have different IP addresses. So you have, I don't know, I can't do the math right now of how many addresses you have, but it's a lot. I want 16 million maybe. And then IPv6 is just this with 128 bits, which is, as everybody knows, is an astronomical, it's a lot of bits. /24 is the smallest, or depending on how you look at it. There's no routes on the internet that are more than a /24. So there's no /25s on the internet. It's called the default free zone, which just means you don't have a default route. And instantly, there's about 1 million public IPv4 routes on the internet. So how do we actually start? So we said that we introduced this to make servers easier to get to. So let's say now once we have those networks now, and we've assigned some subnets to them, and you see they're kind of the normal ones we have. And so now this is when a router comes in. Notice I have at no point previously mentioned a router at any point in my talk. Because if you are talking over layer 2, there is zero purpose for a router. But now when we're starting to want to talk between subnets, we need a router, and that's literally all it does. It's simply another layer 2 device that sits on that's attached to the switch. And when we say the packets go through it, all that really means is packets destined for another subnet. Now, for most of us, if you're on a local network, other packets are usually destined for the internet. So we think of packets as flowing through the router. But often, if you're just talking to a device on your local network, like maybe some I don't know, Echo or one of the Google devices, or even file sharing, that's just switch traffic, right? There's nothing, no firewall is preventing you from doing it. So usually you often will have a router and a firewall together, but again, those are completely separate things as well. And so a reminder that, that since IP addresses are not identifiers, how are they used? This is kind of what a routing table would look like on most computers. I've kind of added a bunch of extra ones, but so you might have, for somebody may have added some local 1042 routes, and those are going to have one. You see, one's a /16 and one's a /24. So if we had say 1042 1010, that would use the second one, and otherwise like 1042.55 would use the top one because it hasn't been sucked in by those bits. But notice that, so here 192.168.18.0.26 here is considered link local. Link local is basically what we've been talking about the entire time. What link local means is I am going to need to drop a layer 2 frame on it to talk to it. And then you have 127.0.0.8. Once again, it has a sort of a next IP, which is sort of itself, and then it's a local thing. So it's basically, all local just means is that it's going to be served by an application locally. The kernel's not even going to leave the system. And that's fundamentally what having an IP address means. You route a bunch of packets, and eventually you get to yourself, and you go to route it, and you just route it to yourself. And then finally, what we call the default route, which is really just 0 bits of internet. And I screwed up here. I wrote it as 192.168.1.1 as the default gateway. But in my example, it should have been more like 192.168.18.1 because of that third row. Because the thing to note, your router always must be layer 2 communicatable. If it wasn't, then you sort of have a bit of a circular problem. So your router is always just another device on your network. And so these get matched in highest number of bits first. That's why 0 is the lowest. That's why it's the default. Is basically, if there's literally no bits that match, you end up using the default gateway. So this is how, this slide I made yesterday, because I wanted to make really one point. And that's the 2 purple ones, is that if you were to do a packet capture of sending messages to any IP address, the only difference between those will be the destination MAC address. So if you were to packet capture a standard TCP dump packet capture, you're going to see whatever you're sending to. Until you add -E, or I guess Wireshark will show, but if you add a -E, suddenly you see the difference between what routing is simply dropping a packet to the device that's claiming to route that, which is the same as delivering it to the device that has claimed that it can handle that packet. It's simply just a matter of which MAC address you send it to. So you're tunneling you're tunneling the IP packet to a MAC address that's claiming to be able to handle it. And so for whatever reason, this blew my mind the first time I realized that there's nothing special about routing other than you're handing it a packet. And so really the interface handles, I have the bottom, you send via the interface. So if you have a tunnel interface, so let's say everybody now uses VPNs. So VPNs won't tend to ARP, they'll tend to, you drop it onto the interface and it uses like ton tap interfaces, which allow them to, they know how to communicate over layer 3 tunneling, which if you want to see a terrible, maybe my next slide, basically I have an IP over email demonstration on my GitHub where I show, again, you can encapsulate packets over anything. When you encapsulate, the idea of encapsulation is the layer you're encapsulating could not care less who's encapsulating it. So, for example, I just show you could base64 encode your IP packets, email them, and just have something receiving that and dropping them back onto the wire. And so now we start to see this is the internet now, right? We now have some network, and then we have these sort of other ones, and we just popped a bunch more routers in between. And you can see these hops if you use a trace route, which probably most people have run. If you haven't, it's a great way of sort of seeing what's happening. But to be clear, all it's showing you is your path out. It confusingly may seem like it's also about your path returning to you, but it's not. And so you drop it to your routers, they're connected together, and eventually packets get. And each one is simply takes those routing table. Again, these are just computers on layer 2 networks. In this case, they're connected together, but they're still ARPing for each other. They still have routing tables. And then they happen to get those routing tables from BGP rather than static routes or whatnot. And so I have a demo that, again, I found that like trying to show these demos was a mess. I do not have the skills. So there is a demo where I essentially show another way of hiding your traffic. So let's say that somebody has a policy where two systems on a local network are not allowed to talk to each other, but they're allowed to talk to the public internet. So once again, IP addresses are not special. They're not identifiers. The only difference between routing and sending a packet is the MAC address. So you can just route via the server that you would like to handle that packet. The other server just adds that IP address as a interface on its site, saying it's loopback, so that it delivers it locally. And then when you go to send to that public address, it's being quote unquote routed to your neighbor's server. Well, from its point of view, there's no routing. It gets it. It says, hey, cool, I have that IP address. I'll deliver it. And if you did a packet capture, all you see is layer 3, because again, nobody does -E. Nobody goes and, even if you do -E, which, sorry, I keep saying -E, that's how you see the layer 2 portion of the frame. Even if you do, I don't know who's memorizing MAC addresses, right? So even if you did do it, you wouldn't even know what to look for. But so essentially, you can use routing to have two machines talk to each other over layer 3 and have packet captures look like it's example.com. And obviously, you could do this maliciously as well. You could, so this is actually a later attack, which is a bunch of VPNs have a vulnerability where if there's a public IP address, that's associated with a local, a link local route, they won't encrypt the traffic. And so you can have a rogue DHCP server or anything that gets a route onto your computer that says to route bank.com or whatever over that, or whatever site you're trying to hide would go that way. And so you can also add a /31 address, which basically just has 2 IP addresses, onto your network. That'll make it a link local route, and then the other one would just ARP respond to it. So you have 2 different ways of getting these same packets. And so this is going to be invisible to layer 2 inspections. And this is this is essentially IP smuggling, right? You're smuggling IP frames over layer 2. Yeah. So the things I want to take you about that is that routing is really about layer 2 encapsulation. You use layer 3 information, but routing and all this delivery is always layer 2. Or the thing that it's always the layer you're encapsulating onto. They're not identifiers, and never assume that a private IP address means that your traffic is not being looked at. Assume every single layer 2 packet you send is being seen by all the devices on the network. If anybody's in a Starbucks or any sort of open Wi-Fi, interestingly, those will warn you about that. But I think a lot of us treat our local network as if that's not true. Or maybe we just assume that the devices on our network are trustworthy. But if you're running a corporation or some sort of small office where somebody can just insert some dongle into something that is now on the network, you now have that thing seeing all your traffic. So can you protect against this? Yes, of course you can. So again, none of this is new. Everybody's known about this. So you can do ARP snooping, DHCP snooping and binding, static ARP or IPsec. So these are all, again, mostly things that you do on a managed switch. And what these do, so what DHCP snooping does is it essentially says, hey, I noticed that the DHCP server responded with this IP address to this MAC address. I see something else trying to ARP for that. No, you don't get to do that. And then you can also do DHCP trusted servers, which really is the way to go, is you say only this port is allowed to respond. Only packets that come in on this physical port are allowed to respond to the DHCP ARP. Because I know that there's a DHCP server that we own on the other side of that. Otherwise, any server can respond to DHCP, which those who were here earlier saw that happen at the hotel. So if you want to learn more, I think DHCP is really cool. Like, you'd be shocked at the number of configuration options within DHCP. It's really part of what's called the BootP protocol. Learn about BGP. BGP is really cool. That's how basically you convert these routes. OSPF and ISIS is sort of like rather than doing static routes between routers, you do these what's called an interior gateway protocol, which basically is it's really neat. It uses Dijkstra's algorithm to identify the shortest path between routers. MPLS, RSV, PTE, LDP. As you start getting deeper and deeper, this is how like backbone networks talk to each other. And Anycast, which coming from a CDN background, my brain exploded when I learned about Anycast, which is really just that. I think unicast IPs are a special case of Anycast, because fundamentally routing is always local. At no point in that routing is there some big giant routing table, right? Routing tables are local, which means if you get an IP address, all you're doing is routing to the closest interface that you can get it to, and that's how Anycast. So if you use 8.8.8.8 as your DNS, you notice anywhere you ping it in the world, it has basically going to have the same response time. That's not because they've have faster light travel, because it's actually responding close to you. And if you want to learn about IP, and GRE, and VXLAN tunnels, WireGuard is one thing. Though, like WireGuard is a tunneling protocol, not a VPN protocol, and that's why you add things like, most people, if you use WireGuard, you end up having to do a bunch of manual configuration to create your VPN, or use Tailscale, which gets you a VPN, or one of the other ones. And also VXLAN. So I had said that you can't have multiple physical separated layer 2 networks talk to each other, and I was kind of lying. VXLAN is the way to do it. It lets you bridge layer 2 networks over IP. Probably kind of terrible, but it is a thing, and it's very common if for some reason you need to span your layer 2 network. And as I said, you can even encapsulate your IP addresses in email, which again, terrible. In my little test using Gmail as my server, I had a ping time of 16 seconds, which is terrible. But you notice on that server, I had all those routing. Wow, I actually have no. I'm going to. So IP is very unreliable, or sorry, it makes no guarantees about reliability. So as you have all those hops, you can start losing packets, and so that's why we introduced flow control. TCP is a stream of bytes that applications use. So this is where every application we use is communicating over TCP. It's sending streams of bytes. It doesn't know anything about packets. It's just encapsulating IP, and you're reading and writing bytes. And so if you want to learn more about that, look into three-way handshakes, congestion control. This is a huge field. Like the amount of work, if you watch the kernel threads, the amount of stuff that, let's just say, Google and others submit in the open source to make TCP better is kind of amazing. And it's encapsulated over IP, so once again, we're losing more and more bytes. So that's why when you see 1448 segment sizes, that's because we're now encapsulating. Now, ideally, if you have a jumbo frames network, you can be dropping 8,000, like 8668 or whatever, something like that is what that looks like here. So finally, we get to layer 7, the part that we all operate in. So we're sending messages and responses, right? And that's going to be interleaved, it's going to be over TCP, right? And there's a lot of layer 7 protocols. Obviously, this one's not the only one. So here's what HTTP looks like. And if you guys went to, I think, Ben and Prashant's talk, they did an amazing demonstration of request smuggling and HTTP stuff and really showed this very well. So hopefully this doesn't overlap too much. And so this is basically this is literally what your browser sends. If you were to use Netcat or Telnet or whatever, you can just go and type basically, essentially something like this, and this is HTTP, right? And so you see in there that the first one didn't have a content length, which implies a content length of 0. But the other one had a content length of 14 for the response, and we send that amount of data, right? This one sends a post data with 12 bytes, and the other one responds with 0. We can also use chunked encoding, which basically means I don't know what the length is, but I know how big this chunk is I'm going to send it to you. So you basically just encode a bunch of chunks. And most request smuggling is usually about this. So usually when you read all the stuff online about request smuggling, it's going to be about chunked encoding and content length stuff. That's not what this one's going to be about. So just a quick reminder, this was kind of what our situation was. We could hit some URL, but if we tried to tell it to use the secret site, we would get a 404. The front end just has no idea what it is. Maybe somehow we have access to the back end, but it tells us no. It denies our request. And so we want to get to that. And so this is kind of what the traditional smuggling attack looks like, is you're changing, you say it's 71 bytes, but it's also chunked, and they get all confused, and then you get your secret response. And so we've now desynced, we've sent 3 requests. The front end saw 2, the back end saw 3, it responded, they're all out of whack. And so the thing is, HTTP is carried over TCP, which is carried over, which remember is the stream of bytes. And so that's had to get framed into requests. And how is it doing? It's using those content length, right? Remember, it's a stream of bytes. At no point does HTTP have anything to do with the packets that you're sending. And so what if you framed it in the wrong spot? Each side is deciding where to draw these lines. And so really this ends up being about this confusion of where to draw the frames. And so Aaron Brown gave this amazing talk on homophone attacks, and the phrase he used in there that I absolutely loved was confusion attacks. And I think this is one of them. The idea of using this, the way of sending data to create different interpretations is amazingly powerful, and it's really about that framing. And so really, how does it work? So let's just say we have this situation where we have some front-end server, and so the attacker basically shoves 3 requests into the TCP buffer. And so it looks like this. This is, if you were to do the packet capture, I would love to have shown this as a live demo, but desync attacks are really super fragile. And so this is basically what's shoved into the TCP. This is a single IP packet, and it has what looks like 3 requests, right? So this attack is against a patched version of Varnish. So this is but off-the-shelf version of Varnish that was patched. But you notice it has connection content length. What that means is it tells Varnish, hey, just FYI, I need you to do your own content length header. But Varnish doesn't have a reason to do that. So it essentially is going to see that, and it's going to decide not to do that. But the front end sees this request for 92 bytes because it says, wow, I have this really cool big request for public site. Let me pop that onto the wire. So then it sends to the back end. You see in there, if you look on that, the exported for, it adds a header that says, hey, here's the IP address that's talking. But you see smuggled into it is this one that also has an exported for with a private address that we want to get to. But what you don't see is a content length header. Content length header is now gone. This is the packet capture from the backend's point of view. So now the backend server then draws a line after the blue request. So from Varnish's point of view, it dumped a request on there. And so the backend sees a post with content length of 0. And so now, so it then puts the response on the wire and everything's good. And you see the front end logged that as a content length of 92 for the same request. And so now we have it's going to read that private request. Now keep in mind, this does not need to be like you pulling private data. This could be you submitting a post. This could be a delete. This could be anything whatsoever to some back-end system. It responds to that with 765 bytes, drops that onto the wire. You see all these private headers. And then the front-end site now has that third request that was waiting. It says, cool, I have this totally cacheable, super benign request for a public site. Let me drop that onto the wire. Meanwhile, already in the response buffer is the private data. And so in this case, we just did a benign request for /secret store that we want to store it on. That gets sent over to the end user, and boom, they have the treasure that you were trying to block with your IP protection. So basically, if they don't agree, terrible things happen. So the thing to note is that most application protocols are request response. TCP is stream-oriented, which means you need framing. There's no relationship between the TCP IP packets and the requests and the responses. Do not assume that because the packet capture looks like that has anything to do with reality. So smuggling allows you to tunnel through a trusted endpoint. So you need to have zero, basically what they call, zero trust security. You need to enable signed requests. Every single request should be signed or some way protected. Do not assume because it came through a quote-unquote trusted endpoint that it's somehow magic. This is user input. Think about XSS. Think about SQL injection. You now have unsanitized input flowing through your system. And so again, this VPN local net CVEs, while I was building this talk, SMTP smuggling came out, which is again, same thing. Line feeds were being used to delimit where requests should be. They get confused. You can now send an unvalidated SMTP message between servers. And basically a bunch of stuff is insecure. Also, domain fronting is really cool. It's another example of confusion here. So yeah, thanks to a bunch of people, including my wife. Any slide that looked good is because my wife, and anything that was bad was because I was hurriedly making it during the conference. And so yeah, I can reach here, and hopefully I maybe possibly have time for a couple questions, maybe. Thank you. Oh, here's if you want like kind of a link to the slides and stuff here.
So I think of protocols as coming in a couple of categories. The old style is you take a data buffer, you cast it to a C struct, and you pray to God that everything was right. The middle tier is I'm inventing a new protocol. I want to connect to a port with Telnet and type commands by hand and get a response that makes sense. Mm-hmm. And I guess the new generation is data binding, where you have some wiring coding like protobuf or thrift. It seems that a lot of these attacks happen in the middle layer, like or there's a different category of attack. The C struct one, obviously you send a negative integer. The middle layer, we do the protocol smuggling. And the new generation seems a lot more robust. Should we be having a movement to replace all of the old protocols with something which has a fundamentally robust wiring encoding and start again? Yeah,
so the question was basically, can we stop having these middle layers that are sort of messing with the protocols as we're passing between system and have a more robust protocol layer? So we have like HTTP2 and QUIC, which kind of solve for some of this in the sense that, at least in terms of the byte framing, HTTP2, which it will, essentially, the framing is not controlled by the user. You're sending the bytes, and QUIC is also a little more tied together to within the individual framing. Problem is, you can always do downgrade attacks with HTTP2. You can then just say, oh, you know what, I can't actually talk HTTP1 in my backend. So I think the answer is yes. You should always be using protocols that are either untrusted or find a way where you're not allowed to allow the user, an untrusted user, to define aspects of your message layout or whatever. Because even with binary protocols, you always have a potential issue. So yeah, I think yes is the short answer. Thanks.
First of all, great talk. Second of all, co-sign what the previous person said, protobuf all the things. My question is actually something you kind of anticipated, which is, how does this stuff look different in a world where we're increasingly getting QUIC and other kinds of streaming protocols? Do you think these attacks go away over time, or are there just things where we haven't discovered quite how smuggling attacks look like in the QUIC world?
Yeah, so the question is basically, within the new paradigms like QUIC and HTTP2, like, just smuggling go away? And I mean, really, I think the confusion doesn't go away. So there was recently what's called a reset attack, a HTTP2 reset attack, which essentially relies on the fact that there's a delay in the, so HTTP2 has, it's basically kind of creates TCP on top of HTTP or on top of TCP. And so you have this idea of the backend saying, hey, I can't really handle any more requests. But there's a delay in the time between the front end doing it and the back end doing it. So the front end's actually allowed to send thousands and thousands and thousands of requests to the HTTP2 server before it starts responding, and then basically you can kill it. So you can still, I think there's always room to use the protocol or delays or anything. There's always going to be some way that the protocols can be abused. And maybe it's not the byte framing, but it's timing framing, or within HTTP2, you can also do cyclic attacks where you have self-referential streams. So thank you. That's my time. Thank you so much.